This is an exciting date for us. This is our 3rd year anniversary as a user group, so I'm pretty excited about that.
You forgot the cake.
Yeah, I know.
Pizza cake.
Yeah. I looked on our meetup site today, and we have 193 members, so that's pretty cool. All right. Next
Yeah, we
month,
don't have a room for that.
we have Mark Mahoney will be giving a talk about state machines and state-based design. So I will post that soon. And also, Ralph will be doing another talk in our series of principles of product development. So that's kind of a bi-monthly thing that we started up. So also, thank you to our sponsors, Always Follett Software Company, for hosting the event. And thank you to everyone from Follett who helped set up the room, let people in. And thanks to 8th Flight for providing pizza tonight. Those of you who are new to the group, the bathrooms are right over there, so you know. And yeah, I'd like to introduce Bob Martin as our speaker. Very excited to have him back at the user group, and I'll let him start his talk about Monads and Clojure.
Okay, good, thanks. What was it, a year ago I was here?
A little more, maybe.
A little more?
Yeah. Architecture, right?
Yeah, was it architecture?
Just 2 years ago.
Maybe that was 2. Well, okay, so I want to talk about Monads. And who here knows anything about Lisp? Good. Who does not know anything about Lisp? We're going to fix that. The rest of you know what? Java? Who knows Java? C#. You all know Java. Same language. So let me tell you the basics of Lisp. And it's pretty simple. Here is a function call in Java. And if you want to make it a Lisp function call, you take that parenthesis and you move it here. Now you know Lisp. That's all there is to it, right? You put the outside parenthesis, that means call. And then that's the name of the function, and followed by the other arguments. So I could say f of 1, 2, 3, 4. Oh yes, commas. You can put them in if you like. Doesn't matter, you can take them out too. Commas are white space. So put them in if you really want to see them. If you don't, that's fine too. How do you declare a function in Clojure, in Lisp? Clojure, by the way, is a dialect of Lisp that runs on top of the JVM. So you can call Java functions from Clojure. Clojure can call Java functions. You can compile Clojure code down to .class files, put them in .jar files, and call them, and no one will know. So if you want to do it in Java, in Clojure, you can. There's also a .NET version of Clojure. It's not quite as advanced as the Java one, but it's catching up, I suppose. Now let's see. I want to declare a name in Lisp, in Clojure. And I do that this way. I define x as 1. This is similar to the Java statement x equals 1. Sort of more like this, actually. More like a declaration with an initializer. Because we don't do assignments in Lisp, in Clojure. We can initialize variables. We cannot reassign them easily. There are sneaky ways, which we're not going to explore. So you say that. Now, one of the things you can do in Lisp, in Clojure, Lisp, same thing, is I can define some f, just a name, f, variable, to be a function which takes an argument, call it x, and, let's just say it multiplies x by x. Count by parentheses here. Okay. Everybody gets concerned about the parentheses in Clojure and in Lisp. Right? There are fewer parentheses in Lisp than there would be, say, in Java. It's just that the ones in Java have different shapes. Right? Now, to fix that, Clojure adds multiple shape parentheses. So you can have square parentheses or round parentheses. That seems to make people happier. Right? There's actually a semantic difference here, but we'll talk about that maybe a little bit later. What I have done here is I have created a function named nothing. There's no name for it. But this function takes an argument and it multiplies the argument by itself. This is the multiply function. It's passing the x variable into the multiply function twice. So this function is essentially the square function. Perhaps I'll name it SQR. And I've taken that function and I've put it into a name, square. So now I can do this. And the result of that would be 25. Now this is a little inconvenient, so there is another form that you can use. Don't try and erase with that. There's another form that you can use that looks like this. DEFN, that's define function. Now I can say SQR. I can say takes one argument. Multiply XX. One less parenthesis to worry about. Same exact statement, just a little bit condensed. That's part of the magic of Lisp, that you can take something like this and then write yourself a little tool that turns it into something like that. You'd think that was part of the language. It's actually not. It's actually a little macro that does some magic behind the scenes. Clojure and Lisp are functional languages. What does it mean to be functional?
Functions are first class type.
Yes, that's what everyone always says. The functions are first class. This is an obscure way of saying, I don't know what the hell a functional language is, but functions are first class, whatever the hell that means. So a functional language is a language in which you cannot mutate a variable. A variable cannot be assigned. It's a functional language. Now, they call it functional because functions are first class, but no one knows what that means, so never mind. You cannot assign a variable. There is no assignment statement, no way to change the state of a variable, theoretically. There are ways to cheat, but we won't do that. How can you write reasonable programs without changing the state of a variable? Most programmers would kind of scratch their head over that for a very long time and think, well, it's impossible. You have to be able to change the state of a variable. And the answer to that is, no, you don't. You never have to change the state of a variable. You can create a new variable. You can pass variables around as arguments. You can return them from functions. You never have to actually change the state of a variable, which most programmers go, I don't understand how that works, and we're not really going to address that much here, just a little bit. Why would that be important?
Multi-core.
Yes, and why would that be important for multi-core?
You can separate out all the different calls.
What's happened over the last 10 years? My laptop here has a clock rate of about 2.6 gigahertz.
4 cores.
Yeah, 4 cores. 4. If they say it has 8, it doesn't. They lie. It's got 4. They talk about some, virtual hyper-threading thing. They're lying through their teeth. There's 4 cores in here, and maybe they've got some little hardware that tries to pretend like there's more than that. The laptop I had before this had 2 cores. The one before that had 1 core. Why are the hardware designers doing this?
Moore's law broke down.
What's that?
Moore's law.
Moore's law broke down. Moore's law, which said that the speed of computers will double every 18 months. But that stopped in 2003. Clock rates haven't gone up for 10 years. Now that's in comparison to doubling just about every year for decades before that. So we slammed into this brick wall of clock rates, which is really the speed of light. You get the parts small enough and enough parts on the chip, and the speed of light is a certain speed, and just to get the signals around, well, you just can't run the chip any faster. They can crank the clock rate up a little bit. You can get to 3 gigahertz if you want, but the chips run real hot, they burn up, yields are really low, so they said, the hell with that, and they cranked it down, back down to about 2.5, and they started multiplying cores. In essence, the hardware people said to us software people, we carried you bastards for decades. Now it's your turn. Right? You're going to make this code go faster. We're just going to give you more computers. And that's a problem for us because for decades we have lived in this fantasy world where there's one giant processor in the sky and we can execute our instructions in sequence. And then we invented this concept of threads. Who's good at threads? Yes, good. All right, so that's the right answer to that. Nobody's good at threads. And I want you to think about what a thread is. A thread is something that the operating system creates on your behalf. And it coddles it, and it makes it nice. It feeds it little registers. It makes sure that the thread can run in a safe environment, stops everybody else, loads all the registers. Okay, thread, you can run. And then it stops the thread and sets it aside, packs away all its registers. It's doing all this work for you. Multiple cores don't work that way. The operating system is not sitting there coddling the cores, stopping them, packing the registers away. The cores are independent of the operating system. The cores are competing at the bus, at the hardware level. And they're competing with a language that sounds like this. I want a byte. Give me a byte. Here's a byte. Take the byte. I want that byte. Here's this byte. Take that byte. Here's this byte. There's no control over this. They're just beating on the bus as fast as they can in a highly competitive environment. If we're bad at threads, how are we going to deal with cores, which don't have any of the controls or disciplines that threads do? And what's going to happen to these cores? You know, my next laptop will have 8 cores, probably. The one after that will have 16, and then 32, and we know where this sequence goes. Are we all going to be programming on computers that have 1024 cores? In another 5 years? 1024 cores? Another 5 years after that, is it going to be 16 384 cores? 32 768 cores? If you were to transport back to 1968 and tell me, a young, very young software developer, that I would be carrying 128 gigabytes in my pocket, I would have laughed you out of the room, right? Because that's impossible. 128 gigabytes, come on. But over the course of time, these scales have gotten away from us. We now live in a world where a terabyte is
$100.
Yeah, exactly. Okay, a terabyte. Well, let's talk about real memory. You know? So, if I propose to you that in a few years you could be dealing with processors that have 32 768 cores, that sounds absurd now. It may not sound absurd in 5 years. And how are you going to deal with that? How will you write code that executes fast on 32 768 cores? How do you take advantage of that computing power when your whole mindset is execute this instruction, then this, then this, then this, then this? Something has to change. Now, what is it that makes threads go wrong? Why do threads fail?
Contention, memory, sliding back and forth.
Good, yes. Contention with memory going back and forth, yes. Concurrent update. Right? Concurrent update. One thread writes something, another thread writes something, one overwrites the one the other one did, and nobody knows this happened. Right? So we have locks. We create these locks, these semaphores. Don't modify that variable until I'm done with it. Don't read that variable until I'm done with it. And then I'm done writing, and then the next guy can read it. And if you ever forget your locks, then it all screws up, and life is terrible. In order to change the state of a piece of memory, you have to have an assignment statement. If you don't have an assignment statement, you cannot have concurrent update problems. You will not use semaphores. There cannot be any threading issues so long as you don't assign. So if you don't assign anything, you don't have threading issues. You don't have core issues. And now the problem simply becomes, how do I take all my functions which do not assign anything? They initialize, but they don't assign. How do I take all my functions that don't assign anything and just split them up onto 32 768 cores? This is the direction that we're all moving. We don't know it yet. We're all moving in that direction. That's why functional languages have gotten interesting in the last 5 or 6 years, why people are starting to dig out the old books from 1957 and wonder what those idiots were really talking about. How much, who's got a laptop in the room besides me?
Everybody.
Everybody, yeah. Where am I? How many of you have a spinning disk in that laptop? Is there something rotating in there?
At the moment.
No, I mean, he's saying yes, he does. Does that machine have a rotating disk in it?
Well, it has a hard drive.
Is it actually spinning? Is it a magnetic disk that's spinning?
Yes.
Yes? Oh my God. I used to ask that question frequently, and 2 years ago it was like nobody had solid-state memory except a couple of guys, and they snickered. And now, of course, everybody has solid-state memory except for a couple of poor guys that haven't quite figured out that they should not have rotating memory. No one should ever have rotating memory again. And how big are the solid-state devices? There's half a terabyte of solid-state memory in this laptop, and that's small now. No, it's not. Well, it's $1,000, maybe $500, but it's worth it. Worth every damn penny. Because I can reboot this machine in 13 seconds. That means a lot to me. Means a lot to everybody. The problem is that disk or solid-state memory is getting cheaper and cheaper and cheaper very rapidly. Moore's law is still working there. And so the notion of 20 terabytes of RAM is no longer ridiculous. Why would we ever get a disk again? And that question will get louder and louder over the next several years. Why would you ever buy a disk again? It's mechanical. It rotates. You have to wait for the disk to come around under the heads. How 2000-ish of you?
1960.
What we're going to face, you and I as programmers, is this world where all of our data is effectively in RAM. Some kind of RAM. Now, it might be flash, it might be something else, but it's in solid state, and it will be very, very fast. And that has an implication that's very scary, because we all use these things called, what are they called? Databases. Who's using a database? Ooh, everybody. Okay, now, why do we have them? These database things.
Store data.
To store data.
And access them.
And access it.
Make it easier and faster to get to where the spinning part comes under our heads.
Yes!
Do I get a prize?
Yes, you do get a prize. You get to hear me say, yeah! Databases existed. The original reason for databases is that disks were slow. And these metal things spin around. It takes a long time to get the data under the heads. You got these arms that seek in and out. Very first disk I ever saw had platters that were 48 inches in diameter. The platter was a good 3/8 of an inch thick, solid steel, dead flat. And it spun. Now, this is a disk of metal, and they had like 12 of them on a spindle. It had to weigh a ton. Literally, 2,000 pounds. Spinning at high speed. Think of the kinetic energy here, right? Spinning like, 10 times a second, maybe a little faster than that. So maybe there was 100 millisecond rotational latency. They actually had several heads around the outside so that the rotational latency would be minimized. The heads themselves were pneumatically driven. There was about a half-second seat time on those heads. And they had this glass window where you could stare in there and watch the heads doing this thing. It was cool. It was very cool. The spindle was suspended on mercury bearings. And the whole thing was the size of a really big
Washing machine.
No.
Refrigerator?
No.
Furnace?
Industrial furnace. It would have been filled about half that wall. It was big, a big monster. And when you started it up, it sounded like a jet airplane. And the floor would shake. And then it would settle out at high speed, and all the vibrations would damp. And you think, oh, thank God. We walked by one day, and I'm a kid, maybe 18 years old at the time, and walked by and looked at the bottom of it. There's little metal filings falling out the bottom. So we called the maintenance dude over and said, is that right? And the guy, the blood drains out of his face. He runs to the phone and he calls the repairman. The repairman saunters in an hour later. He says, yeah, shut that sucker down. Mercury bearings have drained. I saw one of these things cut loose once, went right through a concrete block wall, and bend itself into somebody's Cadillac. You don't want to be around. This thing will level a room. We had databases built to deal with mechanical devices of that nature. But those mechanical devices have disappeared. And they are all but gone. In another few years, they will be gone. And we will have nothing but RAM. And large amounts of it, that'll be persistent. We'll never have disks again. And if you don't have disks, why do you need tables? Why do you need a database at all? Why wouldn't you just store the data where you'd like to store it as a programmer anyway, in RAM? Address it with arrays and pointers, stuff like that. You might need index tables and hash tables and so on, but why would you use SQL? Why would you do any of that? Because it's all in memory for you already. And assume that there is so much of it that you don't have to worry about saving space. Now, if you didn't have to worry about saving space, you would never have to delete anything. Just assume that you'll never delete anything again. If you've got a customer record and the customer changes their address, you don't change the address. You create a new customer record and you expire the old one, but you keep it. You put a little timestamp on it and say, well, that was the old one, here's the new one. You never throw anything away, you always keep it. And if you did that, then you could do this cool thing. You could set the clock back on your database. You could say, well, what did this database look like last Thursday? And get a view. What did it look like 10 minutes after that? Oh, it looked like that. That'd be cool. You'd never lose anything. A database like this, you know what CRUD stands for, right? Create, read, update, delete. A database like this is a CUR database. Create and read. No update, no delete. And if you do not update and you do not delete, you don't need transactions. Because there cannot be concurrent update problems. You're not updating. No concurrent updates. Just read and create. This is the direction we're going again. And notice how similar it is to the idea of no assignments. We are rapidly approaching this time when we will not be assigning variables, we will not be updating data in offline storage, if there will be anything offline storage. Everything will simply be creations and reads, a functional view of both the computer and our offline storage. This is the direction things are going. By the way, have you ever used a database like that? That never forgets anything? Your source code control system. Works exactly that way. Never forgets anything. You can set the date back anytime you want to see it. We've been doing that for a decade, maybe more. If it's good enough for us, it ought to be good enough for our customers. So, all of this was in preparation for this. What the hell is a monad? And I didn't use AH, I used an F. Let. So in Clojure, you can do this. You see that I've got a function defined up there. It's a function named f. And my function named f takes no arguments. Let me get my laser out. Yeah, that's good. And then it uses this let thing. And if you look at the let, you'll kind of get the idea. The let says, well, A can be a 1, and B can be A plus 1, and C can be A plus B. So these are kind of like local variables inside the function. That's what they look like. Right? A is a local variable initialized to 1. B is a local variable initialized to A plus 1. C is a local variable initialized to A plus B. And then I return A times B times C. That's how you do that in Clojure. A times B times C. Fine? Lovely? And if you'd like to see that run, you can see the output down here. I ran it. Here, I'll run it again. Yeah, okay. Little F down there, it returns a 6. What is that? Now, in any normal language, that would be part of the language. It would be a keyword. But that's not what this is. That's not a keyword. That keyword doesn't exist in the language. That's something else. That's a function. How would you write a function like that? Wait. How do you write anything without local variables? This would declare local variables, but what if you can't declare local variables? How could I write this function if you cannot declare local variables? And I can write that function like this. Okay, now this gets interesting. See all those parentheses? All right, they all have meaning. I've defined a function named ff. I'm going to use my cursor for this because that will help. This function named ff takes no arguments. What does that open parenthesis mean?
That's what the function.
Call. See, it kind of looks like a C. Call. Right? What am I going to call? Well, I'm going to call that function, which takes a variable named A, an argument named A. Let's take a look at this function. I'm going to see the entire scope of that function. There it is. That's the definition of that function. What's the argument that gets passed in? 1. And 1 will go into a variable named A. So now A has been set to 1. Cool. And, hey, this function calls this function. And that function has an argument, which is A plus 1, which goes into an argument named B. Now, A is still in scope. Variable A is still in scope here. It's still, the code knows what A is, so now I have both A and B loaded. And I can do the same thing with the next function, because this function, which takes B, gets called. It calls this function, which takes as its argument A plus B. And now it has all the variables defined. It multiplies A times B times C and returns the result. If I had no way to define local variables, I could still define them this way, just as function arguments. But that's inconvenient. It's annoying. I don't want to do that. So I can improve upon that. One of the things I don't like about this is that the arguments are all backwards, and they're all at the end of everything. I'd like to get all the arguments back up to the front. So let me do this. I'm going to define myself a little function called lit. And my function lit is going to take 2 arguments, a value and another function. Okay, now your brain is about to get screwed. Right here, this is where it's going to happen. The lit function calls the argument and passes in the variable. And now I'm going to define FFF to take no arguments. And I'm going to say let 1, and I'm going to pass in a function, which takes A. So 1 goes into A. Now wait a minute. How does that 1 go into A? Because this function is getting passed into let, which will call it. Remember, this function gets called. So this lit gets this function, and it calls it with that. And so A gets defined. And then what does this function do? Well, it's got another lit, which it passes in a plus 1a, which will get into B. And then that will call another lit, which does a plus AB, which will get passed into C. And then I can do my little expression again. So I can get the order right just by putting this cute little function in there. And that function will let me get the order just right. And now how hard would it be to write a little bit of code that took that and turned it into that? Same data, same order. All I have to do is put a few extra parentheses in and a couple of lits. Yuck. But I could do this. I could do this. I could write a little thing that would translate that into this. And I could get all my local variables defined as if they were local variables with this nice syntax. And in fact, there's a way to do this. That's called a monad. The monad is the thing that does this. And the monad that I'm going to talk about here is called the let monad. Now, by the way, that is the let monad, but we're going to create it like you can create any other monad. So we're going to create another monad that does just what let does by doing this. There's this lovely little macro called def monad. It does some magic. I'll describe that magic to you a little bit later. The name of the monad is going to be let-m. We're going to pass in a function called bind. Notice the bind function is just that little lit function. Remember that lit function? Well, that's just the bind function. Why do we call it bind? Because the lit function binds that name to that value. It's the binder. It binds that variable to that value. So we call it the binder, the bind function. Fine. Here it is again, just named as the bind function. There's another function called result we don't need to worry about for the moment. I've set it to identity, which is just this plain old pass-through. So don't worry about the result yet, just the bind. And now I'm going to say, fine. Do the monad, let underscore m, and there it is. There's my structure. And that little monad will take that apart and restructure it to look like this with my bind function in here instead of lit. And it'll execute. That, you can see that mf returns a 6. That's a monad. And now you're asking, so what? Who would want to know anything as stupid as that? That's just a bunch of function calls in and out and people rearranging function calls and trying to wire things up in weird ways. Well, a little more interesting than that. So let me tell you about maybe. The maybe monad. See that fragile function up there? Takes 3 arguments, adds them together. I called it fragile, and you can see why. What would happen if you passed a nil in? Well, let's try it. Who wants to guess? What will happen when I pass in? Null pointer exception. Somebody said NPE. Yes, it is an NPE, null pointer exception. Remember, this is all running in Java. Okay. So Java exceptions come out of Clojure in a very friendly way.
As friendly as job exceptions.
Oh, much friendlier. Wait till you see what some of these things come out as. So I'm going to comment that back out, and I'm going to run that again. And this time it will run all the way through this try-catch block. Now, this is a try-catch block enclosure. Very simple. Looks just like a Java one, doesn't it? Tries with this print line. That should throw an exception. I will catch it. I will print ouch and print the name, and you can see that it printed ouch and the name down here. Now, I don't want that. I don't want this function to have to be exposed to nils. And so I could probably surround it in some function that did a bunch of if statements, checking all the arguments to make sure there aren't any nils. But there's another way. What if our bind function checked and said, well, if it's nil, stop, don't call any further. If the bind function detects a nil, we will just stop cold. Here's the bind function. And notice that it takes a function with a value and another function. That's the way bind functions work. But it says if the value coming in is nil, return nil. Otherwise, go ahead and do this cute little trick of calling the function with the variable. If the value coming in is a nil, it will not call the next stage down in line. So if we were to back up one, go back to let, and look here, it's as though that LT function had that if statement in it, and if the argument passed in, the 1, was a nil, it would not make this function call. It would refuse to make that function call, and the entire downstream would just get short-circuited. It'll just return the nil. So we go back here. I say, okay, this bind function will check the value, and if it's a null, just return. Otherwise, go ahead. And now what I can do is this. I can create a new function called safe_fragile, which takes A, B, and C, and it does the no-nil monad, taking A and moving it into safe A, B moving it into safe B, C moving it into safe B, and then calling fragile. And if any of these are null, it will abort before it does this initialization and return a nil from the entire structure. And in fact, you can see what happened when I executed it here. It returned a 6 from this call, and it returned a nil from that call. It did not throw the exception. So it never got to the call to fragile, which is nice. But you look at this and you think, yeah, but if I'm going to have to write that, I might as well write all the if statements. Well, there's another cute little thing you can do. You can lift. Lifting is when you say, I got a function. This function takes a certain number of arguments, in this case, 3. But I want those arguments to be filtered through the monad. So I want you to lift this function into the no-nil monad so that all the arguments are now protected. So I say with monad, no-nil, lift fragile with 3 arguments, and put that into a new function. So it actually creates a whole new function, essentially this. Just builds that for me. And I can lift it into a safe place. And now when I run it, you notice, first execution here gives me a 6. The second execution gives me a nil. No exception was called. Now that's interesting. I was able to take a function and with a single statement surround it with a wrapper that manipulated all of its arguments and protected it and filtered it and so on. We could think of this as a kind of elevation. I have picked this low-level function up and created a new higher-level function that has protections around it. Cool. In fact, we're going to take advantage of this idea of lifting. And we're going to say that functions can take low-level arguments, but a monad will raise those arguments to a higher level. So what are the two levels in the case of the maybe monad? This one here, this no-nil monad. Well, the low level is possibly nil. The high level is no possibility of nil. So I'm lifting the arguments. What's another kind of lift? Well, here, let's do this. Let's say that at the low level, I have functions that take numbers. But there's a different way to represent a number. I could represent a number in a higher level form. The number 1 could be represented as a single dot. The number 2 could be represented as 2 dots. This is a higher level form of representation. Can I take any function that takes numbers and lift it so that it takes dot notation and returns dot notation without modifying the functions at all? And I think I can. Here's my dot monad. Everyone should have a dot monad. The bind function is very simple. Here's the incoming value, which is a bunch of dots. Here's the function we're going to call. We will call that function and convert to the lower level, counting the dots. And now the result comes in. Now the result is the function that translates in the opposite direction. The result says, give me a number, and I'm going to turn that into a bunch of dots. That's what this apply, stir, repeat, end dot does. Just creates a bunch of dots. And now I can do this. I'm going to create a function named add dots. And I'm going to say with the dot monad, lift plus, which takes 2 arguments. Plus is not an operator. Plus is the name of a function. Right? Functions in Clojure can have all kinds of weird names. You don't have to make them alphabetic. Plus is a perfectly valid name. It happens to be already defined as the add function. So I'm going to lift the add function into add dots. I'm going to lift the star function, the multiply function, to multiply dots. I will lift minus into subtract dots. And I'm even going to do something a little more complicated. I'm going to create this function called DCD, which stands for decade. And I'm going to lift this horrible function right here, which takes 2 arguments, tens and units, multiplies tens by 10 and adds units. And now I'm going to run this. Add dots, 2 and 4. That should make 6. Multiply dots, 3 and 4. That should make 12 dots. Subtract dots, 5 minus 2. That should make 3 dots. And decade 3 and 5. That should make 35 dots. And I think I can run this. And it prints my dots for me. I have lifted these functions, these plus, times, minus, and other functions that take numbers. I have lifted them to deal with dots. The monad is doing both the translation in and the translation back out, which is kind of cool. Okay. So if you've got 2 different forms, and you've got a set of functions that deal with form A, you can lift them to deal with form B anytime you want. You want to do this for Roman numerals? Do it for Roman numerals. Okay. So that's kind of cool. But not even scratching the surface. Because so far, all of our bind functions have simply called the incoming function once or no times. What happens if you call the incoming function more than once? Well, that would lead us to another kind of monad, the list monad. The list monad, the upper form is a list. The lower form is an element, and we will call that numbers. So I've got functions. You can see this function here that adds two numbers. Can I lift it so that it adds two lists? And what does it mean to add two lists? If I were to add the list 1 and 2 to the list 3 and 4, what would I get? What does it mean to add two lists? And what I'm going to do is I'm going to define it this way. I'm going to say that the result of adding these two lists ought to be 4, 5, 6, 7. 1 plus 3, 1 plus 4, 2 plus 3, 2 plus 4. Did I do that right? No, that's 5 and 6, right? 2 plus 10, 2 plus, yeah, 6. 4, 5, 5, 6. 4, 5, 5, 6. In every combination of couples. All right, so my bind function. My bind function is, well, you're going to pass this function into me. I'm going to map that function over my list. This is the list. That value right there, that comes in right there. There's the list. I'm going to map the function you hand me over the list. So that means it's going to call this function, f, for every element of the list, and it's going to return a list of all the results. And then I apply concat to that. I'll tell you why I do that in just a minute. The result is going to take the result of something like this, plus x and y, which will be a digit, and turn it into a list. So if the result of plus x and y was 6, then this will return it into a list with a 6 in it. That list with a 6 in it will come out of that map. The map is right here. And what I would get out of the map is a list of lists. And then I will apply concat to the list of lists, which will just flatten the list. So I can run this. And notice what I get. I did my do monad on list m, and I passed in 1, 2, 3, and 4, 5, 6 with plus x and y, and I got 5, 6, 7, 6, 7, 8, 7, 8, 9. Which, by the way, is identical to this statement in Clojure. This is a more common statement in Clojure. People do this all the time. They use the for function. And what does for mean? 4x in that list and 4y in that list return all the possible additions. Who's done any Ruby? List comprehensions, right? If you've done any Clojure or any other kind of language that deals with lists, this is called a list comprehension. A list comprehension makes perfect sense when you read it this way, but it's just this. List comprehensions are just the list monad applied yet and again to all these things in the language that you might have thought were keywords. They're not keywords at all. They're just functions constructed out of monads. I can make a mul list if I wish and multiply everything together. Did that down here. Ooh, I lifted it. What did I do? I lifted star using the list monad and gave me a list multiplier. Now that's interesting, but let's do one better. Anybody here play Dungeons and Dragons?
It's required by law.
Ever? Yeah, of course. So we're going to play a little Dungeons and Dragons here. Here's a monad called the distribution monad. There it is. You see it right there. This is it actually comes with Clojure. It's one of the standard monads you can use. It translates from a simple sample, that's the lower form, into a probability distribution. Now, how do you translate from a sample to a distribution? If you wanted to know the probability distribution of a die, how would you translate samples into the distribution? You'd roll the dice. count all the rolls. Measure the number of results, and you plot them out in a histogram. That's exactly what this does. Right? That's what we're going to create. We're going to take something that does a sample, that scores a sample, and we're going to run it through essentially a histogram creator. In order to do this, we're going to begin with this lovely function right here, uniform. Uniform creates a uniform distribution between 1 and n. And notice that I specified n. So a die of n sides is a uniform distribution from 1 to n. And now I can define a number of dice. A 4-sided die is just a die n of 4. A 6-sided die is a die n of 6, and so on and so on. Who remembers all the polyhedral dice? Right? 4-sided, 6-sided, 8, 12, and 20. Those were the sides. I can print that. Let's do that. I'll run this. You can see what this looks like. D4, this thing right here, looks like that. That's the probability distribution of a 4-sided die. It's got a 1/4 chance of being a 4, a 1/4 chance of being a 3, a 1/4 chance of being a 2, and a 1/4 chance of being a 1. A D6, well, has very predictably a 1/6 chance of being any of those. But now I'm going to do something cute. I'm going to say, all right, I want to know what the distribution of 2 dice is. So I create 2d2 with a die coming in. And I will use the distribution monad. I will take my incoming die, and I will add the 2 samples together. Remember, a monad takes an upper form and translates it to a lower form. The upper form is the distribution, the lower form is the sample. So I input the distribution, but I'm adding the samples. And then it will turn that back into a distribution. And I created a bunch of these, 2d4, 2d6, 2d8, 2d12. Remember Dungeons and Dragons? Roll a 2d8. And I printed out the distribution for a 2d4. You can see it right here. You got a 1 in 16 chance of getting a 2, a 1 in 8 chance of getting a 3, a 3 in 16 chance of getting a 4, and so on. So that's cute, right? Added up all the distributions. Very nice. So now we're going to play the game. Here's our scenario. Our scenario is the player walking through a map. The player must first encounter a door upon which he must dispel magic. If he does not dispel magic on the door, he walks away dazed and confused. But if he does, there are 2 monsters behind the door, and he must attack both monsters and kill both monsters. If he manages to kill both monsters, then there is a sorceress behind the monsters, which he must please somehow. And if he manages to please the sorceress, she will step aside and expose a treasure chest. And if he opens the treasure chest, he must save against a trap. If he saves against the trap, he gets the treasure, otherwise he gets poisoned. Now, these are all the die rolls. This is the die roll to dispel magic, the die roll to kill the 2 beasts, the die roll to please the sorceress, and the die roll to miss the trap. These are samples. I would pass numbers in here. I'd pass a 1, a 5, a 6, a 12, a 3 into there. And then I would run the algorithm to see which of these outcomes took place. We have to roll a d4 and score a 4 to dispel the magic. To kill the beast, to kill beast 1, we've got to score 15 or better on a d20, and 15 or better on another d20 to kill the second beast. Otherwise, we're going to get eaten. To please the sorceress, we're going to have to roll a 20 or better on a 2d12. Otherwise, we're going to be frozen by the sorceress. But if we please her, then we get to the treasure chest, and we're going to roll a 2d8. We got to score a 10 or better to miss the trap. Otherwise, we get poisoned. If we don't get poisoned, we win. And now, with the algorithm for determining the outcome based on a single sample, I'm going to plug in the distributions of all these dice. And I'm going to say, well, dispel magic is a d4. That's a distribution. Kill Beast 1 is a D20. That's a D20. A D2, D12, and a D2, D8 passing into my scenario function, which takes samples. And when I run that, you can see the outcome. You got a 3/4 chance of being dazed and confused. If you get past that, you got 91 out of 400 chances to be eaten. After that, you got 129 chances out of 6,400 to be frozen, 21 out of 20, 40, 80 to win, and 27 out of 20, 40, 80 to be poisoned. Now that's cool. It did the whole distribution out just by applying to Monad. I didn't have to do the math myself. The math was done by the translation in and out, from sample to distribution, back out to sample, back down to distribution, through a number of iterations. When I run this, notice that it takes it a while to get that last line out. Even on my hyper-fast 4-core super-duper machine, it takes a little while. One last Monad. I made the statement earlier. Can you really write programs that don't assign variables? The answer to that is yes, but some of you don't believe this. So now I'm going to write a program that assigns variables in a language that does not assign variables. I will write a program that assigns variables without actually mutating any state anywhere. You do that with yet another monad. This is called the state monad. The state monad, which is part of the standard library of monads, translates, and it's very simple. It translates from a form, the lower form is just a number, say. The higher form is that number coupled with a dictionary. And that dictionary has all the state variables in it. And when we run through our little process, what will happen here is it will call these functions and pass in our state dictionary. And a new state dictionary will come out and get passed into the next one. And a new one will come out of that and get passed into the next one. So state will appear to be changing. What's really happening is that the state dictionary is getting replicated. New state dictionaries are created at every step along the way. The monad, in its funny little function calling scheme, catches the state vector and pumps it into the next function call. Here are our functions. I'm going to set the value of t to 1. I will print the value of t. I will get the value of t and put it in this nice little local variable. I will increment the value of t and put it back into t. That's the step that should be impossible. And then I will print t. And you see down at the bottom, t is 1, then t is 2. I did that demonstration to prove to you that you can write any program you like in a language that does not mutate state, because you can simulate the mutating of state, as long as you have finite size dictionary. Finite based on the size of your machine.
Because you're not Uing or D'ing the state.
Correct. I'm putting a symbol. I'm using a symbol to reference what I think is the state. Now, how do we know our computers aren't doing that now? They're not. But they could be. They could be. Could I write Java in Lisp? Could I write a Java simulator in Clojure and never mutate any state? I could. You wouldn't want to write any code in it. You wouldn't want to see it execute. But you could do it. It is possible to write fully stateful programs in a language that is 100% functional. You never have to save the state of anything, even if you want to. You don't have to. looking at the state monad hurts your brain. There's function calls and function calls with that call functions that return functions that call other functions. So I'll leave that as an exercise for you to look at it another time. Are there any questions? No, of course, everybody's perfectly happy. Yeah, go ahead.
Are there two types of functional programmers? Normal programmers and people who write monads?
There are people who use monads, and all functional programmers use monads, whether they know it or not. Let is a monad, for is a monad. There's a whole bunch of monads that you use, you just don't know if you're using them. Then there are those rarefied few, and I'm not one of them, who writes monads and conceives of monads, like that distribution monad. I thought that was kind of unique. And the state monad, when ever use that? But I think that's probably true. Or rather, I think there are functional programmers who have not written a monad yet, and will eventually do so. Who's written any functional code? Some of you. Okay, good. Keep doing this. You're going to have to learn it. Unless, of course, you're going to go into management. Anybody else? No?
Okay, what about C++ templates? Could those do the same thing?
Yes, because they're completely Turing complete. So you could write a Lisp compiler in a C++ template, and then write monads in that Lisp compiler, and then write a Java interpreter in that Lisp running in the template compiler.
I want to see that.
Yeah. Hey, listen, I mean, who amongst us would have believed 20 years ago that we would all be programming in a simulator? Right, and we all do now. Virtual machines are all just, and nobody would have believed that 20 years ago. It was, no, it's ridiculous. You need to run on the metal.
So in the state monad was always one of those things that, like, I'd get about 75% there and my head would explode.
Yeah.
Like,
Yeah.
So I'm just trying to sort of understand, like, because you're not defining it here.
I did not
You're just
define it.
using it. Okay. Is it?
I can show you what it did.
Yeah. Like, what's the binder and the returner for that? Like, well, so like the get, print, and set that you have there. Those,
Yeah.
Are those like? Are
Yes.
those operating on the lower level, the upper level?
So the get function is indicative. It's kind of a hint of what the bind function and the result function are. The get function, which you see down here,
Yeah.
looks like it gets the value of a variable. What does it really do? Okay, well, what's coming in is the key for the variable.
Right.
The get function returns a function. That's where it all automatically starts to get hard.
Yeah.
The get function returns a function, which will be called by the state monad. The function accepts the state vector. This is the dictionary.
Right.
And then it returns a list of two things. The return value of get, which is just the lookup of the key,
Yeah.
and the state vector.
Yeah.
Right? So the state vector goes in, and it comes right back out.
Right.
Print does exactly the same thing. It just returns the same state vector as well as printing. Set is the interesting one.
Right. Okay.
Because set changes the state of K to V. And so here, what it does is it returns a function that accepts the state vector, gets the old value of K, and then associates into the set vector, the state vector, the new value of K, and returns that new updated vector, that updated hash, in the return value. And
So
I've
these all
already said too many
return
words there.
So they all have to return pairs, basically,
All these functions actually return the
to
pair.
set the chain out, basically.
So the lower type is a variable, an element, a number, or anything that's just one thing. The upper form is that variable plus the state.
Pair, yeah, gotcha.
It's a pair with the value and the state. So the state and the value are always coupled inside the monad. You just don't see that here, because the threading of the monad takes that S argument and hides it from you. In fact, I printed down here the S vector, the state vector. You can see it down here.
Right, that's the resulted of the last thing. The results of the monad returns the pair, so you're seeing the pair.
So given those definitions, you ought to be able to work these monads out trivially.
Would that make it a continuation then?
Oh God, what the hell is a continuation?
Continuations.
Where you pass in like kind of what you keep passing the function, so it basically doesn't resolve until the very end.
Yeah.
What you initially passed in.
Well, it's
It weaves a bunch of function calls together, basically.
yeah.
There's no like interruption of flow. It's the opposite, actually. It's like,
It goes straight down the stack.
yeah, it just
Yeah.
creates the chain of everything.
So what's this I hear about monads being the bridge between pure functional land and the rest of the world? Is that
Insinuating.
Yeah, you are. You're seeing
Okay.
here with the state monad.
Is it anything besides the state monad, or?
So they'll. I don't know an awful lot about languages like Haskell, which are purely functional, and there's a golden glow around them. Who saw Pulp Fiction? You open up the briefcase. Apparently, to do anything that interacts with the outside world, you do it through some kind of monad. I presume that that's a state monad, something like this, but I don't know that for a fact.
It's like a state monad. It's called the I/O monad. So in Haskell, basically everything that can interact with an external system is done through the I/O monad. So it basically is. It's not really pure functional, but it lets you write. So basically, like if you're going to do a get from like the keyboard, right? Your world basically is part of that monad. So it's like conceptually is like what the world was before you typed hello and what it was after, But in that I/O monad is where the read happens from the external system, and that's irreversible. You can't that's like the only thing you can't reverse because you're doing things that can actually change external state. But that helps at all.
Anybody else? Yeah. Oh, yeah.
Do you see this as being like a software paradigm that will be used in all types of applications, from web to robotics to like everything?
I do, yeah. I don't see that there's any limitations to using a language like Clojure or other forms of Lisp. It's a very, very simple, very elegant kind of language. And what I've discovered over the last several years is that virtually anything you want to write, you can probably write better in a language like this. And that actually surprised me. I was not a Lisp programmer for many, many years. I only started doing it maybe 6 years ago. So I was first of all a C++ bigot, a C bigot for years, an assembly language bigot before that, then a C bigot, then a C++ bigot. Then you can't be a bigot when you're a Java programmer. You've already compromised all your values by that. And then somebody said, well, you ought to read this book, SICP, Structure and Interpretation of Computer Programs. And I bought the book and I put it on a shelf, and I thought, well, maybe one day I'll read it. And then the one day happened, a miracle enough. I picked the book up one day and said, all right, I'll read the damn book. And the book just thrilled the hell out of me. And I still have these moments of remembering reading this book, just throwing the pages and reading page after page. It had been a long time since a computer book had excited me as much as that book did. And of course, that was a book about Scheme, which is a Lisp variant. And it wasn't really about Scheme. It was just about programming in general. And I drew the conclusion that, wait, there really is something. All these Lisp heads for decades had told me that it was a great language, and I always told them to go to hell. And then I thought, oh, these guys are right. There is something to this language. So nowadays, I do an awful lot of programming in Enclosure. Who watches the videos that I do? Some of you do. Cleancoders.com. Go there, watch videos. They're much worse than these talks that I do here. And that whole website that we sell those things on, it's all done in Clojure, up from bottom to top. It's all just done in Clojure.
Can you show us that?
Can I show it to you?
Everything that I've seen in functional anything is all these fascinating toys.
Well, that's what people always show, right? So let's see if I can show you what that Clojure code looks like. Let's see. Open recent cleancoders.com. There we go.
You signed an NDA before you came in, right?
This is not. Okay. That one's not a particularly interesting one, so let's look at something a bit more interesting, like order. You can see these functions here. They're here. And you can see what they look like. They're just regular old Lisp programs. Yeah, go away, dumb thing. But let me show you something that might have a little bit more meaning for you. Let's go into a controller. Let's go into the Codecast controller. Yeah, I know. And let's close that. Now, you can see down here at the bottom, there's this thing called def routes. And def routes, you should recognize it instantly, right? It takes a URL. There's the URL coming in an HTTP request. And what it does is it binds that. It says, okay, pull this data out of the HTTP request. So it just gets it out. It treats the HTTP request sort of like a dictionary. Pulls these arguments out, and then it calls that function. Show codecast. Let's see if we can slide to the right. Show the codecast based on the permalink. Where did it get the permalink? Got it from here, which was just one of the HTTP arguments. What does show codecast do? Well, that's up here. And, there's a let function there. It's going to go and say, find the codecast by permalink. That's a database call. And it's going to put that in codecast. And then it says, if the codecast is published and, it says and code, if the codecast exists and it's published, then let the images be the images of the codecast. Let the viewer be the active viewer. That's a function that finds the active viewer. Let the cart be, if there is a viewer, then get the open cart for the viewer, otherwise nil. Let the licenses of that viewer be the license statuses of the viewer for that codecast in that cart. Let the children of the codecast, and you can see it goes and gets the child codecast because codecasts can have children. And if we might have a parent too, so we'll get the parent. And then it says render template. This is the output side. Render template with this dictionary of values going into the template. Now, what does that template look like? You're going to like the template. Because the template is down here in the views. If I can find the views. There we go. And I want the codecast view. How about that one? And don't worry about this up here. That's just a bunch of boilerplate. Look at that stuff. Now, that's not HTML, but it is HTML. It's just HTML written in Clojure. And it generates real HTML, except of course I can put code in it. So while I am constructing the HTML, I can do little function calls inside of it and other little stuff. Out comes all the HTML. Now, think of what a web system is. Web system is a request coming in, bunch of processing, HTML going out. So every web request is a function call. It takes inputs, produces outputs, just like any functional program would be. Little in and out there, but there's not much to it. Yeah?
Are those periods there parts of the function, or the symbol names, or are those?
The colons?
Cascade, no, like TD dot label, is that all the symbol name?
Where are we looking at?
Well, I'm
26.
Yeah.
Oh, TD.label, that's, what is that, a class?
Yeah, it's a Clojure keyword. You can have dots in it, and it just rips it apart and makes it a class. Yeah.
Oh,
Yeah.
cool. Okay.
That's a CSS class, right? Is it a class or is it a
CSS
ID?
class. Class.
The pound is the ID, the dot is the class?
Yeah.
Yeah. I try to not remember as much as I can about CSS. Yep.
So I know the history of the syntax of Lisp has got a pretty long history. Has there been any attempt to create a language that's more like an imperative language that we know, that has the exact same principles, but maybe looks more like a C-based language?
I don't know if there has been. And maybe somebody else here would have a better insight into that than I do.
And is the reason that one doesn't exist if it doesn't because this really is the best way?
It's certainly been very persistent. Lisp has tried to be killed many, many times, and it keeps on coming back. One of the reasons for that is this. The structure of a function looks like a list, because a list looks like that. That's a list of 3 integers, but look at that. That looks like a list with a fin and whatever that is and whatever those is. And in fact, it is a list. The code of Lisp is written in Lisp's own data structures, which means that a Lisp program can manipulate itself simply by manipulating the tokens in its own lists. So when we say a macro in Lisp, what we're really talking about is a program that takes in another program and manipulates it to emit a modified program. So this is a macro that takes in that, but emits that. That's a very simple case. And actually, it's not that simple, but never mind. That's a simple idea. The def monad, do monad, with monad, those things that I was using, those are actually macros that construct that chain of function calls that I was showing you. They actually build it and then execute it. That's an attribute that only one other type of language I know of has, which is assembly language. Assembly language is written in its own data structure, and Lisp is written in its own data structure. I don't know of any other languages like that.
It's just that the only data structure in assembly is the number.
Okay.
But yeah.
All right. Well, Lisp is a little more complicated than that, but it still has that same attribute, which is called homoiconicity. Yes, that's a homoiconic language. I have a feeling that's going to be important. Just a little inkling. I think that's going to be important going forward. None of our current languages behave that way. All right, we should probably kill this before it breeds. So, thank you all for your attention. Appreciate you listening. Is there still pizza back here? Yep. Good. It's gold. Best kind.
Thank you very much. Back to the device.